Today we are going to study rotational kinematics, which is basically the chapter 8 of your textbook. Now, rotational kinematics is a word having two words, that is rotation and kinematics. First of all, we are going to study the word kinematics as we already know about it from our last chapter that kinematics is the study of motion without the reference of forces. In short, you can say when we are been discussing the motion with respect to the geometry, we call is kinematics. But when we are studying the motion with respect to the forces, with forces, we called it dynamics. Now the question arises, what is rotation? Rotation is basically the motion of a body in a circular path along a fixed line or axis. We are going to study this in detail in our this chapter. Now this is the basic outline of this chapter. First header which we're going to be discussed is rotation motion. The second heading is rotational variables, which includes angular displacement, that is theta. Second, angular velocity, omega. And the third one is angular acceleration, that is alpha. In the third heading, we have been going to discuss rotational quantities as a vector, whether they are vectors or not. In the fourth heading, we are going to discuss rotation with constant angular acceleration. And then the last heading, we are going to discuss the relationship between an angular and the linear variables. Now, we are going to discuss the rotational motion, the motion of a rigid body. Now, the question arises, what is a rigid body? Rigid body is a body in which there is very less deformation or there is no deformation. And the other definition or the main characteristic of the rigid body is the distance between the 2 points inside the body is always remains the same. That is point 1 and that is the point 2. The distance between any 2 points in the body remains the same is called as a rigid body. Now, the motion of the rigid body when every point in the body moves in the circular path around a line or axis of rotation. In simple word, axis of rotation is the point or the line around which, yeah, about which the body rotates is called axis of rotation. Now we are coming again to the definition. The motion of a rigid body when every point in the body moves in the circular path around a line or axis of rotation is called rotational motion or angular motion. And the example of it is the spinning wheel, which we used to see in our daily life every day. Now the next header which we are going to discuss is rotational variables. There are the three main rotational variables. That first is angular displacement, the second is angular velocity, and the last is angular acceleration. Now, what is angular displacement? The angle formed at the center of the circle between its two radii when a body rotates and rotates an axis of rotation is called angular displacement. Now, the four main keywords has been highlighted. The first is the angle formed at the center of the circle between the two radii. Now let's see this figure. Now the first radii is this and the second is this. Now the angle formed, that is an angle, okay, between these two radii is called as angular displacement as stated in our definition. The SI unit of angular displacement is radian. The angle suspended at the center of the circle between its two radii is equal to the 1 radian when arc length is equal to radius of the circle. When arc length is equal to the radius of circle. Now the explanation of our definition. Consider a particle P is attached at the end of massless rod having length r. Now the particle P is here and the massless rod is this. The particle is attached at the one end of the rod and the other end is called as the center of the circle represented by the C. The other end of the rod is pivoted at C, which I already told you people, which is the center of the circle when rod is rotated. The axis of rotation is normal to the plane of rotation and passes through center C. Okay. The axis of rotation is normal to the plane of rotation and passes through the center C. Now, the rod CP describes a circle of radius R when allowed it to rotate. At any time, its position is CP1, making an theta with reference line CP. After this is our reference line CP. After time t plus delta t, its position is CP2, making an angle theta plus d theta with reference line. The angle d theta is called angular displacement of Cp during the time interval dt. The angular displacement is positive for counterclockwise or you can say anti-clockwise direction rotation. It is negative for clockwise rotation. The angular displacement is a vector quantity having magnitude and direction as well. Its direction is given by right hand rule. The right hand rule for the angular displacement is as similar to the concept which we studied in our other course of electricity and magnetism. As we know that in that the thumb represents the direction of the curl and the curl of the fingers being representing the magnetic field. Here the current is replaced by the rotational component variable and the curl of the finger is representing the rotation. So in short, here we mean the thumb points out in the direction of the displacement and the B where the B is replaced by the direction of rotation. Let's now read from the slide what it's going to say. Hold the axis of rotation in your right hand in such a way the fingers are curling in the direction of the rotation. The thumb is along the angular displacement. The same which have been already explained with a reference to our electricity and magnetism force. Now coming towards a second rotational variable that is angular velocity. The rate of change in angular displacement is called as angular velocity. It is denoted by omega. Its unit is radian over second. Its non-SI units are called degree per second or revolution per second. Explanation. Consider a particle P, which is shown here in the figure, is moving along a circular path in counterclockwise direction as shown in the figure. The angular position of the line OP is theta 1 at time t1 and later t2 is theta 2. The angular displacement of P is delta theta is equal to theta 2 minus 1 during the time interval delta t. Now the average angular velocity of P is written as theta 2 minus theta 1 over t2 minus t1. That can be written as delta theta over delta t. The limit of the ratio delta t when approaches to 0 is called instantaneous angular velocity. It is as similar as we have studied for the linear relations. Omega instantaneous is equal to limit delta t approaches to 0. Delta theta over delta t is equal to d theta over dt. The angular velocity is a vector quantity and its direction is given by the right hand rule. Now we have seen again the same which we have been studying. The curl is representing the rotation while the thumb holds the axis of rotation in the right hand in such a way that fingertips are along the direction of rotation and the thumb is along the direction of angular velocity. Now we are going to see the linear and angular velocity relation. We are going to study this thing again in detail in our last topic of this chapter. Consider a particle moves along a circle of radius r. The arc length s and the angular displacement theta are related as s is equal to r theta, which we have studied in our preceding slides. Definition at both sides with respect to the t, that is ds over dt is equal to r d theta over dt. In the limiting case, ds over dt is called linear speed v and theta d theta over t is called angular speed that has been represented by omega of rotating body. So we have proof v is equal to r omega. Now we are going to present the vector form of this relation. Consider a particle P is located at distance r from the origin in xyz plane. As shown in the figure, the particle P rotates in a circle about z-axis. It means the plane of the rotation is xy axis, having perpendicular distance r sine of theta. The angular velocity omega is directed along z-axis while linear velocity v is along the tangent direction at point t. The linear velocity in this case can be written as vt, that is the as it is in the tangential direction. So here the t represents the tangent. The linear velocity and the angular velocity are related as v is equal to omega radius of the circle, and we have written it like r sine of theta. It can be written in the uh, vector form, that is v is equal to omega cross r. The linear velocity is always perpendicular to the plane defined by the angular velocity and position vector. Now we are going to discuss the third important rotational variable that is angular acceleration. The rate of change in angular velocity is called as angular acceleration. It is denoted by alpha. Its SI unit is radian over second square. Its non-SI unit are degree over second square and revolution over second square. Explanation. Consider a particle P is moving along a circular path in anti-clockwise direction or counterclockwise direction as shown in figure. The angular velocity of body is omega 1 at time t1 and later time t2 angular velocity is omega 2. The change in angular velocity of body is omega is equal to omega 2 minus omega 1 during the time interval delta t is equal to t. The angular acceleration of p is written as, that is an average, alpha is equal to omega 2 minus omega 1 over t2 minus t1 is equal to delta omega over delta t. The limit of the ratio of delta omega t when approaches to zero is called as instantaneous angular acceleration. That has been presented in the form of differential. It can be written as del d omega is equal to alpha dt. Integrate both sides. Now we will end it with this equation: omega is equal to omega naught plus alpha t. The angular acceleration is a vector quantity. Its direction is given by this right hand rule for the two paths and rotational variables. Hold the axis of rotation in your right hand in such a way the fingertips are along the direction of rotation and the thumb is along the direction of angular velocity. The angular acceleration and angular velocity are parallel to each other when angular velocity goes on increasing due to rotation. The angular acceleration and angular velocity are antiparallel to each other when angular velocity go on decreasing during rotation. Now we are going to show the relationship of linear and angular acceleration. The linear velocity v and angular velocity omega of a particle when it moves along the circle of radius r are related as v is equal to r omega, the same relation which we have studied in our preceding slide. Now differentiate both sides with respect to the t. dv over dt is equal to r d omega over dt. In the limiting case, dv over dt is called tangential component of the linear acceleration a, and d omega t is called angular acceleration alpha of rotating body. At is equal to r alpha. The radial component of linear acceleration is ar is equal to v square over r. Now we can relate it within the different relation of angular component that can be written as r square over omega square over r, which is equal to omega square multiplied by r. We can write, we can split omega into two, that is omega, omega, and the r. Now this is equal to v is equal to r omega, so we have put the v and omega is there. Now we are going to say about vector form of this angular acceleration. Considering a particle P is located at a distance r from origin in xy plane as shown in the figure, this is exactly the same figure which we have already studied for angular velocity. The particle P rotates in a circle about the z-axis having perpendicular distance r sine of theta. The angular velocity omega is directed along z-axis while linear velocity v is along the tangent direction at point P. V is equal to omega cross r, differentiate both sides with respect to time. As we already know from our basic classes, then when there is product between the two things and we are applying differential, then we have to apply the product rule. Now the product rule is dv over dt is equal to d omega over dt multiplied by r plus omega plus dr over dt. When we write it in the last form, that is a is equal to alpha multiplied by r plus omega multiplied by v. Linear acceleration a in terms of radial and tangential component, it is written as a is equal to at plus ar. Compare equation 1 and the 2. This is equation 1 and this is equation 2. So we've been ended at is equal to alpha multiplied by r, and the radial component is ar is equal to omega multiplied by v. This is tangential component of linear acceleration and this is the radial component. Now we are going to discuss few examples and exercise problem of the Halliton Resnick book related to this topic. Now this is an exercise 2 from your book. Here we are asking that show that one revolution minute is equal to 0.105 radian second. It's very easy problem as we know from our basic classes. One revolution, basically revolution is the unit of angular displacement, is equal to 2 pi radians, and 1 minute is equal to the 60 second. Therefore, to convert from revolution minutes to radian, multiply by 2 radians and divide by 60 second. The conversion is as follow: 1 revolution over minute is equal to 1 revolution of minute divided by the factor, this factor. So we've been ended with 0.1047 radian second. Round off to 3 significant figure, we've been ended with the required proof. This is the second problem from this topic, which is the exercise 3 from your textbook, Halliday Resnick. It says the angle turned through by the 5 wheel of a generator during a time travel t is given by phi is equal to at plus b t power 3 minus c power t4, where a, b, and c are the constant. What is the expression for angular velocity and angular acceleration? As we already studied in our last slides, that angular velocity is nothing but it's just an omega derivative of angular displacement, and an angular acceleration can easily be found by taking the derivative of angular velocity, or in other words you can say taking the double derivative of angular displacement. Now I'm going to show the details with the putting the values and everything in our upcoming slide. Now this is the expression and now this is our equation. Simply use this formula and substitute the given value. That is delta t over delta t. This is the question. Now simply take the derivative which we already know from our very rudimentary classes. So simply we've been ended with an angular velocity of a plus 3b t square minus 4c 3 t power 3. Now similarly we've been going to take the derivative of this equation and we've been ending with an angular acceleration. It's not velocity, it's an acceleration, which is 6 bt minus 12 ct here. Now we are going to discuss our third problem related to it. This is the problem number 1 from Halliday Resnick book. The angular position of a point on the rim of rotating wheel is described by phi is equal to 4 radian second multiplied by t. So as you can see, it is a speed, but when we multiply with the time, we've been getting the displacement. Similarly, this is acceleration, but when we are going to multiply with the time, we've been getting the displacement. Similarly, it is in the form of 3 cube. So when we multiply it with a time cube, so we've been getting the displacement. What is angular velocity at t is equal to 2 and t is equal to 4? The part B says what is average acceleration, and the part C says what is instantaneous angular acceleration. Now, as we know from our last example and from our derivation, that angular velocity is nothing but this. That is the, the formula which we're going to use in our first part. Now it comes an average acceleration. Average acceleration is nothing but, now keep this in the mind, that there is a profound difference between the average acceleration and instantaneous acceleration. When this delta t approaches to zero, then we say that is instantaneous acceleration. That is average acceleration. Okay. Now in this case, we have been using 4 and 2 second velocity, while here you've been using the expression and taking derivative of it. There is a slight difference between these two parts. It will be clear when I've been solving in a. Now this is the solution which we are going to theory of the problem. The instantaneous angular velocity of the wheel can be found by this relation. We just need to put the value which is given by the numerical for it, and we've been ending with this equation. Remember this equation because we've been going to use this equation in our last part as well for finding instantaneous acceleration. Then angular velocity at t is equal to 2 is simply found by putting the time value, that is 2, and we've been ended with 4 radian per second. Similarly, when we put 4 second, we've been ended with 28 radian second. So we can say the angular velocity at 2 is 4 radian second, and at the 4 is 28 radian over second. Now the similar way we can find then an average angular acceleration by our delta formula, that is delta omega over delta t, and we just need to put the values. That 28 radian per second has been found with 4 second, and that has been found for the time 2 second, and we just have to put the values, and we will end it with 12 radians over. Now, the instantaneous angular acceleration can be found with this formula. We've been using the relation of the equation which we have already found in the part 1. Just take the derivative of 8 and put for the time t is equal to 2 and t is equal to 4. And at the end of the day, will be found for the time 2 is 2 second, we've been getting 6 radian over second square, and for the time t is equal to 4 seconds, we've been getting 28 radian second square. Now we are going to discuss the third main topic of our discussion is rotational motion as a vector. Now you just see in this figure we have a one body body looks to me a book and is placed in YZ plane and is rotating along x-axis. Okay, in the first pass it is rotating for the 90 degrees, and then that similar body is rotated along z-axis with 90-degree rotation. And after these two rotations we've been here in this position. Now we've been doing the same thing for the second part, but first we've been doing the rotation along z-axis, and after that we've been doing the rotation for the x-axis. Now we've been ended with this position. Now look, this position, position 1, is not equal to position 2. It means that we can't write rotations in terms of vector because we know the vectors holds the property of commutative. So this is the equation which we get from the figure. Phi 1 plus phi 2 is not equal to phi 2 plus phi 1. From the preceding figure and the above equation, we can conclude that finite angular displacement cannot be represented as the vector quantity. Wait, where the things is going to change. Now we have changed the rotation size. First it is 90 degree. Now it is 20 degrees. First in the x-axis, then we rotate the rotated body along z-axis of for 20 degrees. Now we've been ended with this position. Now the body again in the same position, first rotated in the z-axis along z-axis for 20 degrees and then in the next axis. Interestingly, we've been ended with the same position as we have in the upper case. So, so from the last discussion and the figures, we can conclude phi 1 plus phi 2 is equal to phi 2 plus phi 1, which is the commutative property and which is the main characteristics of the vectors. So we can conclude from the preceding figure and the above equation, we are in the position to say that infinitesimal angular velocity rotations can be represented as the vectors, or with very small rotations we can easily represent that in the form of vectors.